Swayam Prabha. Digital India. Educated India.
Hi friends, now we will discuss on the topic wind energy, and as you know the wind is nothing but the flow of air or the motion of air, and all we have seen that in case of fan we get air motion and we have apply electricity, then electricity helps the movement of the fan blade, and that is electrical to mechanical energy conversion, and then movement of the fan blade gives some motion to the air. So, that is the air is getting some motion and it is getting some energy inside it, that is the kinetic energy of the air when it is in motion. So, that way electrical energy is converted to the kinetic energy of the air in case of fan. Now, if we can develop a certain device which can work in the reverse principle of the fan, then we can be able to convert the kinetic energy stored in the air into electrical energy. So, the principle of wind energy is this one, and we will discuss more about this wind energy in two classes, and in this class our content is the wind as a source of energy, then wind energy system. We will also discuss types of wind machines, and then energy production from wind and wind energy computation, and the nature of wind and selection of site. Now, we will see wind as a source of energy. As you know that wind is nothing but the motion of air. So, air gets some velocity, and this is because of the uneven heating of the earth surface. Earth surface we have land area, we have water. So, land and water both are not equally heated. So, we know that the land gets heated very quickly with respect to water, and again gets cooled very quickly with respect to water. So, during daytime the land area gets heated quickly and becomes warmer than the water. So, air at the land being warm up goes upward, and the cold air on the water moves towards the land area. So, we get one movement of air or the motion of air, that is called wind. So, that wind is generated in the daytime in that way, and the night time the reverse directions we can get. So, this is the reason why we can get the wind, and this wind gives some kinetic energy to the air, and that kinetic energy we can convert into the electrical energy. And once we want to get the electrical energy or mechanical energy from the wind, then we have to get good velocity of the wind, and we know that the more wind speed, more is the velocity of atmospheric air, and more is the kinetic energy. So, now we will see now the wind energy is the kinetic energy associated with the movement of atmospheric air. It has been used for hundreds of years for sailing, grinding grains, and for irrigation. So, these are the ancient applications of the wind energy, and recent application is the electricity production, and so wind energy systems convert this kinetic energy into more useful forms of the power. Then in 2017 report says that in the world we have 5,39,581 megawatts wind energy production capacity, and the total production of this 5,39,581 megawatt electricity is produced in the world. Out of this around 85%, that is equal to 4,56,572 megawatt is produced in 10 top countries, and rest 15% is produced in the rest of the world. So, if we think about the top 10 countries around the world producing wind energy, the China ranks the first position. It is 1,88,232 megawatt capacity and its share is 35%. So, in China around 35% energy is produced from the wind, and for US the second position 89,077 megawatt, that is 17% share. For Germany the third position 56,132 megawatt and the share is 10%. For India we have 32,848 megawatt with a share of 6% energy. So, out of the total energy produced in the country, we are having 6% of the wind energy. And Spain we have 23,170 megawatt and 4%, that is their share. And then United Kingdom 18,872, it has 3% share, and then France 13,759 megawatt with 3% share, and then Brazil 12,763 megawatt with 2% share, and Canada 12,239 megawatt with 2% share, and Italy 9,479 megawatt with 2% share. So, this is the statistics of the wind energy productions around the globe as per 2017 data. Now, if we think about the wind energy system, then we can get three major terms. One is wind machine, then windmill and wind turbines. So, wind machine convert the wind energy into useful form of energy. There is a very generic common name, wind machine. Then windmill works on the principle of converting kinetic energy of the wind to mechanical energy. So, windmill, when the kinetic energy of wind is converted to mechanical energy, specifically that is windmill, and wind turbines that transform the energy in the wind into mechanical power, which is further transferred into electrical energy. So, the wind turbine is the latest development and it helps to generate electricity from the wind. Now, how the kinetic energy of air is transferred into electrical energy, that is the point we have to understand. So, when the wind is available, when the air is in a motion and we have some windmill, say windmill has some blades, some rotor, and then wind flows, it is blocked by the blades, and then the downwind of the blades, that is some low pressure creation, and that low pressure gives a lift to the blades. That is one force the blade is getting, and another is a drag force. When the wind is blowing and then there is some resistance, the blade is giving some resistance, there will be some drag force on it, and then the drag force as well as the lift both helps to rotate the rotor, and this is the mechanism. The rotor rotates and then the blades also rotates. So, if the rotor is fixed with a shaft, then shaft will also rotate, and that shaft, one side of that shaft can be connected to turbine and then turbine to generator. So, then electricity can be produced. So, the force of the lift is actually much stronger than the wind's force against the front side of the blade, which is called drag, and the combination of lift and drag is what causes the rotor to spin, and this rotating action then turns a generator which creates electricity. So, this is the mechanism through which electricity is produced. Now, the wind power which is available, that is proportional to the cubic root of the velocity of the wind. So, if the wind speed doubles, then the power potential will increase 8 times. So, wind energy technologies use the energy in wind for practical purposes such as generating electricity, charging batteries, pumping water and grinding grains, already we have discussed. Now, we will see the wind energy systems. So, here this figure shows us two systems, one is your old windmill and another is your new wind turbine. So, old windmill we have brick tower, and in both the cases we see the blades or the rotor is placed at some certain elevation. So, not at the immediate surface of the earth, it is put at certain height. So, the height is required because as you go up the wind velocity increases, at the surface there are resistance is more. So, wind velocity is less, if we go up then the velocity will be higher, and more the velocity obviously more will be the energy potential. So, around 30 meters height the windmill is installed here. So, that is the old model, and this is in case of new model we are getting that is new wind turbine. It is the blades are different, the fiberglass blades we are getting, and here we are having wooden blades. So, this is the basic difference between two types of windmills and wind turbine, and for getting optimum efficiency or considerable performance, the wind speed should be 16 to 20 and the height may be at 50 meter. So, these are the typical values which gives us optimum result. Now, we see the wind turbine, the size is say 2 megawatt, from handheld to 2 megawatt capacity wind turbine is available, and typical is 250 kilowatt, and then rotor diameter 25 to 30 meter and tower height is 30 to 40 meter. So, this is the descriptions of wind system, and then we will see here types of wind machines. So, wind machines that helps to convert electrical energy to any usable form of energy. So, that wind machines may be of two types, one is your horizontal axis machines and vertical axis machines. So, there are two types of machines. So, here we see is your horizontal axis machine. In this machine we are seeing here the axis of rotation is parallel to the direction of the wind stream. So, this is our axis of rotation. So, wind is also flowing in these directions and rotor is also there. So, axis, so we see here rotor axis is horizontal and can be adjusted so that it is parallel to the direction of the wind. So, this rotor which we are having here, this is axis is parallel to the direction of the wind, and it is not necessary that every time the wind is flowing in the same direction. So, the direction will change, when the wind direction will change, the rotor movement, the direction can also be changed in this design. So, horizontal axis windmill can further be classified as single blade, double blade and multi blades. So, this blade here three blades we are seeing, that may be single, double or multi blade system we may have. Then we will see vertical axis machines. So, this is an example of vertical axis. So, this is our axis vertical and this is our blades. So, in this case this is the simplest of the modern types of windmill which works like a cup anemometer, and rotor axis is vertical and fixed, and then the machine has become popular since it requires relatively low air speed or air velocity or wind velocity. So, low velocity of winds can even generate electricity by this type of machines with respect to horizontal axis windmill. Now, we will see the comparison between these two horizontal axis and vertical axis machines. So, in case of horizontal axis, a controller is required for proper orientations. So, when the wind speed is changing, then the directions of the rotor will also change by use of some controller. This is very important for horizontal axis machines, but in case of vertical axis not necessary, no controller is required because this is fixed. And then variable speed power transmission for better control, and then simpler power transmission system for the rotor to the axis. Variable blade pitch can tolerate wider fluctuations in wind speed in case of horizontal axis machines, and for vertical the machine performs even at low wind velocity ranging 8 km per hour to 16 km per hour, and the horizontal axis is lightweight and vertical axis it is bulky having much material, and horizontal axis high tower ensures greater wind speed and low height installation leads to lower available wind speed in case of vertical axis. So, it is very clear to us that vertical axis height is lesser than that of the horizontal axis machines. Now, we will see how to calculate the power productions or power efficiency or power potential of wind machines or wind. So, power production from wind. Now, we will see the kinetic energy of a mass of m moving at a speed of v is half m v square. We know that kinetic energy is equal to half into m into v square. So, what will be the power potential? The power potential will be half into mass flow rate. So, this m will be mass flow rate into v square. That means that this much of power I can get per unit time. This is the power potential. Now, the mass of air passing in unit time through an area A. So, this is our area A, cross sectional area, wind is flowing in this direction. So, what will happen in this case? What will the mass of it? Mass is volume into density. So, volume of air into density of air. So, volume of air means area into the linear velocity. So, that is A is the area into V, where V is the wind speed. So, this is our volume of air which is passing through this cross sectional area in unit time. So, that is the V. So, if we multiply it by the rho of air, so this is the mass flow rate is equal to rho into A into V. So, in this expression what we can get half m v square, half m is equal to rho into A into V and V square. So, we are getting half into rho into A into V cube, where A is a constant for this particular A. But this is our power potential, half into rho into A into V cube. Now, the power potential which is available in the wind, that wind will not be converted or will not be available for its transfer, because after getting resistance at the blade the wind will reduce its velocity to 0. That is why the energy which is available with the wind, the complete conversion will not be possible, and it has been proved by different researchers, particularly the Albert Page in 1929. He has recommended and proved that around 59.3% of energy associated with the wind may be transferred in the turbine. So, the power potential we can express, or the turbine power we can express as half into rho into A into V cube, which we had, into some constant, that is Cp. So, Cp is called the power coefficient, and this Cp is the power coefficient. So, what we are getting now, P is equal to half into rho into V cube into Cp. Now, A, Cp, rho and half, or A may change, rho is the property of the wind and Cp is also a power coefficient. So, these are constant, and half into this is equal to constant, we are considering is equal to k. So, this is equal to k. So, k into A into V cube, this is our power potential, and this half into rho into Cp, that is almost around to 0.37. It has been proved by many experimentation, and approximately this can be 0.37 for air. So, if this is, then what will be our total power potential in terms of electricity? So, that will be this into 0.37 into A into V cube into some efficiency factors. This is for wind energy which will be available, then wind to mechanical conversion and mechanical to electrical conversions, and there will be transmission. So, another 3 types of efficiency we have to multiply: efficiency mechanical, efficiency electrical and efficiency transmission. So, that we have to consider. So, overall power will be getting 0.37 into efficiency of mechanical conversion, kinetic to mechanical, and then mechanical to electrical and electrical to transmission. So, then the machinery is used for the transmission. So, that there will be also having some efficiency term. So, this and here V by 10 cube, because this power efficiency we are considering this, the power potential is considered in terms of kilowatt. So, here we are having watt unit, this unit if we want to convert into kilowatt, that is divided by 1000 and that is written V by 10 to the power q. So, V q we had already, now V q by 10 1000 it is there. So, V by 10 to the power q, that has been made. So, this is the expression which is used to calculate the power potential in kilowatt unit when the V is meter per second, the wind speed is in meter per second. So, this way we can calculate the power potential of the windmill. Now, as you know that the power potential is proportional to the V cube, that is the wind velocity. Now, we have one blade. So, if we have a rotor, then we have some blades. So, these blades will be moving and then we will get the energy. So, here this is the blade tip. So, it may be the end of it or any position it may be. So, this wind linear velocity is giving the rotational movement to the rotor and to the blade also, and this movement, the RPM, if will be varying if we have two different machines with different diameter of the rotor, the RPM will be varying. So, to compare these variations in the RPM, in spite of using RPM, another term can be used, that is tip speed ratio. So, tip speed ratio is defined as the blade tip speed meter per second by wind speed. What is the wind speed and what is the blade tip speed we are getting. So, that way we can get one number, and that is easy to compare two different machines. So, this TSR range is 1 to 15 and it is defined as this blade tip speed by wind speed. Now, what is the blade tip speed in meter per second? If we know the RPM, then 2 pi r into n, n is the revolution per minute and per one revolution it 2 pi r, it moves, r is the radius of the blade. So, 2 pi r into n, n is the RPM. So, that will be the linear distance covered by the tip. So, this is the blade tip speed 2 pi r n, and then this is wind speed. So, per minute revolution. So, time is our 60. So, 60 says 1 minute. So, 60 second. So, 60 second into V. So, V is the wind speed. So, now we are getting tip speed ratio is equal to 2 pi r n divided by 60 into V, where r is the radius at which SR is calculated, that is speed ratio is calculated, and V is the wind speed in meter per second and n is the RPM. Now, we can calculate the speed at any position also, it may be r many values. So, that way that is called speed ratio. So, here we have a speed, here we have a speed, because this point has to travel more distance, this point has to travel less distance. So, SR, that is speed ratio, will be different for these two cases because wind speed is fixed. So, that is the concept has been developed to determine the tip speed ratio to compare different turbine blades and the machines. And next we will see the wind shear. So, if we go up, we will see that the wind speed is increased. So, once the wind speed is increased, then obviously the power potential will also be increased. So, there are some mathematical relationships, the people tried to correlate this the increase in the speed with the height, and two types of equations are available, that is logarithmic equation and power equation. So, this is our logarithmic equations. It is clear that velocity unknown is equal to velocity known into ln height desired by beta by ln height known by beta. So, if we have height 1, here is one machines, here one machines we like to put, say this is your h 1 from the base, this is our h 2 from the base. So, I know the say wind speed here. So, it is V 1 and this is V 2, I do not know. So, we will be using here that this is our height. So, velocity unknown, say V 2, it is not known. So, here V 2 is equal to V 1 into your ln height of V 1 that is known and height of V 2, that is h 2, height h 2 by beta. So, this beta is called the roughness constant, and this beta value will depend upon the roughness of the surface and it will vary from place to place, different types of surface, different types of beta value we will get, and those beta value normally ranges from 0.0001 to 3.0 meter. So, it has wide variations in the beta depending upon the nature of the surface. And the other expression which is used to predict the wind speed at any height, if we know the wind speed at any other height, that is equal to, that is your power equation. So, velocity at unknown is equal to velocity of known into height of desired and then height of known. So, height desired means that is for unknown and this is for known velocity and height, and then to the power alpha, that is a power expression. So, this alpha is called the wind shear exponent, and one thumb rule is that this alpha value is around 1 by 7th. So, 1 by 7th. So, a generally recognized rule of thumb is that wind speed increases as the 1/7th power of the height above ground, and here this table gives some example of different terrain and different alpha values. So, it is also somewhere it is 0.10, 0.14, 0.16, 0.2, 2.4, and these are the different conditions. Now, we will see some wind energy computation. So, how the wind energy can be calculated with some numerical problems we will discuss now. Say a horizontal axis wind turbine with 30 meter rotor diameter produces 1 megawatt electricity at a wind speed of 60 kilometer per hour. Then calculate the following: blade tip speed for a tip speed ratio of 4.25, and then overall percent conversion efficiency of the wind turbine from wind energy to electricity. Air density is 1.225 kg per meter cube. So, this is our problem statement. We have to calculate the blade tip speed, that means if we have a blade here. So, this tip speed we have to calculate, and it is given us that our TSR is equal to 4.25, and TSR is equal to, we have come to know that tip speed by wind speed. So, tip speed is equal to wind speed into TSR. So, here TSR is equal to 4.25 and wind speed is equal to 60 kilometer per hour. So, 60 into 1000 meter divided by 3600 per second. So, we are getting now 70.833 meter per second. So, if we convert it into kilometer per hour, then it is 254.9988 kilometer per hour. So, this is our blade tip speed here, linear velocity of the blade tip we are getting. Second, overall percent conversion efficiency we have to calculate. So, now we will see what amount of electricity we are producing here and what was the maximum potential we have here. So, potential, to calculate potential we need to get the value of wind speed, and here we have V equal to 60 kilometer per hour, that we have to convert it into meter per second, and so 60 into 1000 meter divided by 3600, that is meter per second. So, that is 16.6666 meter per second. So, this is our V. Then what will be the theoretical energy available? What is the theoretical energy available? Half into what is this? We need V cube and you need A and we need rho. So, P is equal to half into rho into A into V cube. So, half into rho is equal to 1.225 kg per meter cube, and then A is equal to the area. This is the area, the blade which is having the diameter of how much, 30 meter rotor diameter. So, pi r square, we are having pi r square by 4, pi r square by pi d square by 4. So, we are getting here A is equal to pi d square by 4 or is equal to pi r square. So, this is the area we are having. So, that area we will get here and put this value here, rho value is given here and V value I have calculated here, this one. So, by putting these expressions we are getting the available energy in the wind is equal to half into rho into A into meter cube. So, this is equal to this megawatt, this will be 2.003361 into 10 to the power 6 watt, that is equal to megawatt we are getting. So, this is the megawatt energy available in the wind, and as a electricity we are getting 1 megawatt. So, the efficiency, conversion efficiency we can get 1 divided by 2.00336 into 100, that is equal to 49.91 percentage or approximately 50% efficiency we are getting. Now, we will see another problem statement. So, this is the figure, it shows that one horizontal axis windmill is there, wind, and what we see, the distance is h, and this height and the velocity is related with this formula v equal to q into h square. Then figure 1 shows the variation of the height from the surface of the earth to wind speed. So, this is our velocity and this is our surface of the earth, this is the trend at which the velocity changes with height. Then it is given as k v equal to k into h square, k equal to 1 per meter per second, and calculate the minimum height at which a horizontal axis windmill should be erected to generate a wind power density of 10 kilowatt per meter square normal to the direction of the wind. So, this is our 10 kilowatt per meter square energy potential or energy density. So, that we have to calculate the height at which the mill has to be put. So, now the other information is given, the electrical efficiency and mechanical efficiency of the system are both 0.9, and whereas the transmission efficiency is 0.52. So, mechanical equal to efficiency electrical equal to 0.9 and efficiency of transmission equal to 0.52, it is given. So, what is our case? Our P is equal to 0.37 into m into efficiency of electricity, efficiency of transmission, and then we have V by 10 to the power cube. This is the formula we have. So, this formula we have. Now, in this formula our P is given 10 kilowatt per meter square. So, this is kilowatt per meter square. So, kilometer unit, and then we are having, so A term is not there per meter. So, A is not here, A has come to this place. So, then we are having this m is equal to 0.9, is eta A equal to 0.9, eta T equal to 0.52, and V is equal to how much, that I know, that V divided by 10 to the power cube, this is the expression. So, from this expression we can calculate the value of V. So, value of V is equal to this much, 6 to the power 1/3, that is 4 into 10 meter per second. So, 4 into 10 meter per second, then the 40 meter per second we are getting that V, and that if we get the value of V, k equal to 1. So, h square equal to, we are getting 40. So, h is equal to half of 40. So, that is equal to 6.32 meter. So, at 6.32 meter if we put this turbine, then we will get this 10 kilowatt per meter square power density. Next we will see the nature of wind and selection of site. Nature of wind means whether it will be having sufficient speed or not, that will depend upon many factors, that is your latitude of the place, altitude of the place, topography of the place, and scale of the hour, month and year, at what time, at what in which month and which year. So, all those things will influence the wind speed and the type of wind that we mean. And then suitable sites for the wind energy installation, that is the best sites at offshore and on the sea coast. It is on the, as we know that daytime and night time there will be wind, in both the cases there will be direction of wind. So, at shore, offshore and on sea coast, this is the best place for the installation of the wind turbines, and the second best sites are in the mountains where the height is high. So, air velocity will be more. So, that will also a good location for the installation of the wind turbines, and the lowest level of wind energy is found in plains. So, plains it is not so important or so economic or so feasible to install the wind turbines. So, then for wind turbines it also requires lot of land. So, we need lot of area available for the installation of the wind turbines, because if I put one wind turbine here, so I have to keep some space between two wind turbine for the installation. For example, you see this is our arrangement of wind turbines. So, this is one, another one, another one, another one. So, these and these are rows, and this column also we are having turbine here, turbine here, turbine here. So, this one turbine to turbine distance and this turbine to turbine distance has to be maintained, and people try to understand and then to optimize the distance required, and basically after turbine the downstream of that the wind speed becomes less, and then we need to give some more time to recover this wind velocity and then before reaching to another turbine. So, this gap is necessary. So, once the gap is necessary, the what will be the land requirement, that will depend upon the number of turbines I need to install or the capacity of the plant, the overall capacity of the plant I want to get from the windmills, that should be known to us, so that we can calculate the land requirement. So, a thumb rule says that spacing of turbines between 5 and 10 rotor diameters apart, if prevailing winds are generally from the same direction, turbines may be installed 3 or 4 rotor diameters apart in the direction perpendicular to the prevailing winds, and under multi-directional wind conditions spacing of between 5 and 7 rotor diameter is recommended. And here it is mentioned that a simple rule of thumb, the turbines follow the spacing rule of 4 rotor diameters apart horizontally and 7 rotor diameters apart vertically in the wind's direction. So, we have made some discussions on the wind energy productions, and thank you for your patience.